like to introduce myself. I'm Nigel Gebodh, and joining me as co-chair today is going to be Zeinab Esmaeilpour. We're both from the neural engineering group working with Dr. Maron Bixen, and we're from the City College of New York. So today, for today's session, we're going to hear about MEG and EEG with non-invasive brain stimulation, artifacts, modeling, and artifact removal. And we have a great lineup of speakers today to talk about these things. So I'm going to jump into the first talk, which I'll be giving. And I'll be talking about the characterization of artifacts during EEG and TDCS. Mm-hmm. So as we all may know, EEG and TDCS can be combined, and they can be combined to non-invasively stimulate and record EEG activity at the same time. And they can be combined to identify changes in brain state during stimulation. So you can stimulate the brain and look at what's going on in the brain at the same time. And the combination of EEG and TDCS has been applied in both clinical and non-clinical applications like epilepsy, stroke, memory, sports, attention, etc. Now, one method of combining both TDCS and EEG is with an interleave design. And with an interleave design, what you have is that the HD TDCS electrodes are interleaved with the recording electrodes here. And what this allows for is the recording and stimulation at the same time. What it doesn't allow for, though, is recording and stimulating at the same site. Now, there are several obstacles when it comes to combining EEG and TDCS, and one of the main obstacles is that several artifacts occur in your data. And here we define artifacts as non-neurogenic signals that appear in your data. And prior work has tried to deal with this by using several types of signal processing techniques to attenuate the artifacts. And they've made several assumptions about these artifacts, including that they're narrowband, they're time invariant, they're spatially stationary, they're montage independent, and they don't outlast stimulation. So our motivation with this work was to characterize these artifacts and explore some of these prior assumptions that were made. And in doing so, we identified 4 types of artifacts in EEG and TDCS. And we also use computational modeling to replicate them. And these artifacts that we're going to be talking about include the cardiac, oculomotor, myogenic, and device on-off artifact. And we broke these up into inherent and non-inherent artifacts. And when we say inherent, we mean artifacts that are an integral part of physiology, and so they're always there. And non-inherent are artifacts that are non-integral to physiology, and they can be easily avoided with proper experimental design. So in terms of our methodology, we used 2 stimulation configurations, an M1SO and a bifrontal montage, seen here. And we used 4 different current sources listed here. And our current intensities varied from 0.5 to 2+ milliamps. And these are some of our data collection details and processing details. And so we jump right into the data, and the first thing that we notice for all 4 devices is this large DC voltage artifact. And essentially what this is a voltage offset that's about 1,000 times larger than the baseline EEG. And when we average the DC voltage artifact, what we get is a topography that reflects the stimulation montage that we're using. And when we zoom into the DC artifact during stimulation, what we see is that what we see is that there's about a 3 millivolt drift in our signal over time, over the 50 millisecond period. And this drift was consistent across 3 out of the 4 stimulation devices. Post-stimulation, when we looked at the voltage after the stimulation was turned on, we saw that there was a residual voltage of about 1.5 millivolts max. And we can see some residual voltage in the topographies here. When we looked at the time frequency breakdown of the signal, what we saw is that during stimulation, there was some semblance of EEG activity during stimulation, which is good news, and it hints that we could recover a lot of this signal with good processing techniques. And what we also see is that there's a 1 hertz band that pops up, and we'll talk about what that is later. When we ran our computational models, we saw that we can properly get the same magnitude of the artifact that we saw in the real EEG data. So another thing that we looked at was how the DC voltage artifact changed as a function of current intensity. And what we saw was that it was linear as you increased the current intensity from 0.5 to 2 milliamps. And even when you changed the polarity, it still maintained linearity. Now, the problem with the DC voltage artifact is that if you leave it unchecked, the artifact can easily cause saturation, and it can introduce nonlinearities in your data. And it can also contribute to a lot of data loss. If your amplifier is just completely saturated, you're not going to get any data. So the next thing we did is we looked back at the time domain, and we removed the DC voltage artifact and looked at what was going on during the stimulation period. So what we saw in the time domain was the most striking thing was that the blinks during stimulation were distorted and in some case inverted. We also saw that there was a constant pulsatile rhythm during stimulation. And we saw that these changes were only there during stimulation, not before or after. So several questions arose, including, is this pulsatile rhythm related to cardiac activity or a ballistocardiogram? And can we quantify these changes in these oculomotor responses? Can we quantify how it inverts and how it becomes attenuated? And how do these artifacts change as a function of stimulation intensity and with varying stimulation parameters? So the first thing we tackled was the cardiac relationship. So we took the data, bandpass filtered it, and time locked it with ECG activity. And what we saw was that the artifact was cardiac related. It was time locked a few milliseconds after the peak of the R wave in ECG. We also saw that the artifact was present across different stimulation devices, so it's device independent. And the artifact strongly, when you average all these peaks of the artifact, it strongly reflected the stimulation montage that we were using, which was the M1SO montage. And we were able to get the model to reflect these changes or the artifactual changes, the artifact topography, by changing the scalp conductivity by 0.3%. Now, when we took the artifact and looked at it in the frequency domain, what we saw was that when we compared the EEG in green and the EKG in red, what we saw was that both of these signals were modulated at the same fundamental frequency, which gives more evidence to its cardiac relationship. So we decided to dub this the cardiac artifact. So now the next question was, what happens when we change the current intensity? So how does this artifact change when we change the current intensity? Well, when we did that from 0.5 to 2 milliamps, what we saw was that we can modulate the artifact as a function of current intensity. When we took all these peaks and averaged them, what we saw was that the artifact scaled linearly with current intensity, and we can get that same scaling with our computational models. What we also saw was the artifact's amplitude and spatial distribution was able to be replicated by the finite element model or the computational model. And so the next thing we wanted to do was we wanted to get a sense for how much the data are changing during stimulation and get somewhat of a signal to noise ratio. So we looked at the generalized singular value decomposition, which gives us somewhat of a signal to noise ratio by taking into account both data sets. And when we did this, what we saw was that the artifact during stimulation was at most or about 40 times larger than the singular values during baseline EEG. What this also indicated was that you would have to remove multiple singular values in order to get data comparable to baseline EEG. And the problem with this is that the cardiac artifact is present throughout the stimulation period. So if you look at the whole stimulation period, you'll see all those little pulsatile rhythms. And if you remove multiple singular values, you're basically going to decimate your signal significantly, or you might not be left with anything. And this points to the fact that we need more robust techniques in order to deal with these artifacts and clean them up. And so the next thing we decided to look at was the blink artifact. And so we extracted all the blinks from our during stimulation data and averaged them. And what we saw was that the blink amplitude during stimulation was amplified or attenuated as a function of the type of stimulation that we were doing. So for anodal stimulation, what we saw was an attenuation in the blink amplitude, and for cathodal, we saw an amplification of the blink amplitude. We also saw that during stimulation, the blinks were spatially specific. So this is before, and during stimulation, we see a kind of shift in the topography for one way of stimulating, and attenuation for another way of stimulating. And post, it goes back to being relatively normal. And when we looked at the data in the frequency domain, what we saw was that during stimulation, there was an exacerbated around less than 1 hertz component being introduced into the data. And what we believe this was blink contamination. And we can see that it was closer to the frontal electrodes, and it was closer to the frontal stimulating electrodes compared to electrodes further away from the stimulating electrodes without blinks. So we then looked at how it changed with current intensity. And so what we saw was that the blink amplitude changed asymmetrically. So as you increase current from 1 to 2 milliamps, there seemed to be a divergence in the peaks of the signals. And we can also see little cardiac artifacts being introduced in the data as well. And so what this meant was that the blink amplitudes were modulated or changed as a function of current intensity. So on one side it increased and the other side it decreased. And the blink topography, so if you look at this topographically, you can see a shift more to the right with increasing current intensity. And if we baseline or if we normalize the 1 and 2 milliamp data, what we saw is that we can replicate this type of topography with our computational modeling by doing a few tricks. And so the problem with these changes in the blink amplitudes is that blink removal algorithms, they rely on specific characteristics of the blinks in order to remove them. If these characteristics change, then the algorithms would underperform and we would get this noise introduced in our data, and it would be exacerbated because of the simulation. So again, it points to the need for more robust artifact removal techniques for blink removal. So the next thing that we looked at were the myogenic and motion artifacts. And remember, these are non-inherent. So these are things that you can control for in your protocol. So for the myogenic artifact, what we asked subjects to do was to basically sit and clench their jaws about 5 times. And for the motion artifacts, what we asked subjects to do was to do a rolling neck motion. And this was all done during stimulation. And when we did that, what we saw was that the myogenic artifact, or these jaw clenches, their activity changed as a function of current intensity. So as current increased, we saw sort of a voltage offset on top of the high frequency activity during the muscle contraction. Another thing that we saw was that the myogenic activity was spatially specific. So under no stimulation, this is what the jaw clenches would look like. And when we started to introduce current from 1 to 2 milliamps, we saw that the spatial distribution of the voltage changed. We also saw that it's no surprise that the myogenic activity was broadband and mostly high frequency. So between stimulation and non-stimulation conditions, the high frequency activity wasn't that different. However, at low frequencies around DC, we saw that there were changes from stimulation to non-stimulation. It's mostly probably due to this offset that we see here. For the motion artifacts, what we saw was that there was some broadband and exaggerated activity nearest the stimulation location. So this shows a spectrogram near one of the stimulation locations, and this is an electrode further away. And what we saw was that there was exaggerated activity that was amplified here, and there's a little broadband spike that showed up. And so this is just to show that you should control for these things in your protocol when people are undergoing stimulation. And because the myogenic activity overlaps so much with neurogenic frequency bands, it makes it hard for it to be removed. In general, without stimulation, it's hard. It's a thing that's hard to remove. So with stimulation, it's even harder. And also, the myogenic activity can alter the path of the stimulation current by steering the current, because when you contract your muscles, the properties of the muscle change and it steers the current. It can steer the current differently. So you might not be targeting the area that you think you're targeting. So the last artifact that we looked at was a device on artifact. And not many people realize that this was happening. So essentially what happens is that when you set the person up and they're connected to the stimulation device and you turn on the stimulation device but do not stimulate, what happens is that most devices do an impedance check. And they do an impedance check by releasing a small amount of current and measuring the impedance. And so when it does that, it actually introduces a large voltage artifact. And so you get a large voltage offset in your data. And the problem with this is that it can contaminate your baseline data without you knowing about it if you're unaware of this issue. And it can introduce artifactual fluctuations if it's constantly doing an impedance check during your baseline data. So this is something everyone should be aware of and control for. So just to summarize, what we saw was that there were inherent artifacts in our data, and they're present in all human recordings. They're widespread and cannot be avoided. They overlap highly with neurogenic processes and frequency bands, and they're an integral part of physiology. We also saw that there were non-inherent artifacts, and these are artifacts that can be controlled for in most experimental settings. They're highly disruptive during stimulation, and they can completely decimate your neurogenic data if you leave them unchecked. All right, with that, I'd like to thank you guys for listening. This is our group. Feel free to reach out. And if there are any questions, we can take them now.
If anyone has any question, you can just type it in the chat area. Okay. What do you think is the mechanisms for increased cardiac artifact during a stimulation, Nigel? Nigel, you're muted.
All right, can you hear me now?
Yes, now we can hear you.
What is the mechanism of increased cardiac activity during stimulation? So the mechanism, we're not exactly sure what it is. We believe that the cardiac artifact is the ballistocardiogram, which is actually the vibration of the body with a heartbeat. And when you apply the current, the skin properties change, and there's also some vibrations at the stimulation locations. So with the properties of the skin changing and the body vibrating, we're seeing this this increase in the amplitude of the artifact.
Okay, another person is asking how to deal with these artifacts then.
So to deal with these artifacts, I'm going to let the other speakers talk about that since they have more expertise on that. So you'll hear about how to deal with some of these things in your own data. Okay, so in the interest of time, we are going to just answer one of the questions. What should be the optimal distance between the recording electrode and the stimulation electrodes? I guess that would be dependent on your protocol. I don't really have a good answer for that because if you put them too close, they're just going to shunt. So yeah, that's where computational modeling would come in, and Zeinab is an expert on that, so she would be able to address some of that. I think we're just going to move on to the next speaker, Dr. Lee from the University of British Columbia. And she's going to talk about the removal of some of these artifacts with simultaneous EEG and stimulation. So Dr. Lee, if you'd like to share your screen.
All right. Can you see the screen?
Yes, perfectly.
Yep.
Okay. Good afternoon and good evening, everyone. My name is Susan Lee, and I'm a postdoc fellow at Pacific Parkinson's Research Center at UBC and the Wellcome Center for Integrative Neuroimaging at University of Oxford. I'm happy to have all of you here. So the topic I'm going to talk about is removing stimulation artifacts from simultaneously recorded EEG data. And I'll cover some of the technical challenges and several signal processing techniques to tackle the problem. So to start off, I will briefly explain what the motivation was for me to work on this challenge and some background on the stimulation that we used in the study. So I'm doing research on Parkinson's disease, which is the second most common neurodegenerative disease in the world. And the main feature of PD is degeneration of neurons in the substantia nigra that produce dopamine. So more recently, studies have highlighted that PD is associated with abnormally synchronized neural oscillations in brain regions for motor function. So PD is currently treated with medication that supplies dopamine to the brain. And another treatment option is deep brain stimulation that involves a surgery to implant microelectrode inside the brain. However, it is inherently invasive, expensive, and it has risk for complications. So it's obviously not an option for every patient. So more recently, researchers have been exploring alternative therapeutic interventions that are safer and more easily accessible, such as non-invasive brain stimulation. In particular, our group uses galvanic vestibular stimulation to apply mild electrical current to the mastoid processes behind the ears to modulate the firing rates of vestibular nerves. GVS has been explored as a potential therapeutic intervention for PD since the pioneering study conducted by a Japanese research group in 2005. And since then, several other groups have demonstrated beneficial effects of GVS. However, the studies have reported only behavior effects, and consequently, the effects on upstream neural activity that are responsible for the behavioral changes are largely unknown. So to understand the underlying neural mechanisms of brain stimulation, we need to combine the stimulation with brain imaging such as EEG, fNIRS, fMRI, and PET. And EEG is particularly valuable for non-invasive brain stimulation studies because it is able to record brain activity with high temporal resolution, and we can access the data almost instantly with modern computers, which we can utilize further to explore a more advanced advanced stimulation techniques such as closed-loop stimulation. However, the high voltage stimulation artifacts tend to completely dominate the EEG signals, and identifying ways to properly analyze the EEG acquired during stimulation has been a major challenge to date due to several reasons. So the first reason is that the stimulation artifact amplitude is several orders of magnitude larger compared to the actual brain signals. And here is a real example of EEG recorded during GBS. And as you can see, the eye blink and then the stimulation artifacts that's much larger than the neural activity. So imagine to recover the EEG recorded during the stimulation. So it's gonna be really difficult. And the second reason is that the frequency ranges of stimulation and the cortical oscillations of interest can overlap, which makes it impossible to use simple signal processing techniques such as digital filtering to remove the artifacts. So, for example, in this study, the authors measured individual alpha frequency from each subject and delivered tags at the individual alpha frequency. And then they wanted to look at the changes of phase and power at that frequency, which is impossible. So what they did is they instead looked at the EEG recorded after the stimulation was turned off. So that's what's most commonly done in the research for now. And third reason is that the stimulation artifacts recorded downstream in the EEG do not exactly match the delivered currents at the stimulation electrodes. So we can observe phase shifts, magnitude variations, and other morphologic alterations in the EEG. So in this slide, I plotted some real example of artifacts that are recorded across different channels. And as you can see, there are 180-degree phase shifts, and amplitudes are different depending on the distance from the stimulation electrodes. And if I plot the artifact recorded as single channel across 6 different trials, you may think that, oh, they look exactly the same. But in fact, if I zoom in carefully, the phases are slightly different, amplitude is also different, even though we delivered exactly the same stimulation. And if you look at the amplitude differences, it's around 10 to 15. And if we look at the neural activity at that the same channel, it's almost the same magnitude. So if we are not able to remove artifacts properly, then it will cause issues in the EEG analysis later on. So because removing stimulation artifacts are challenging, so people have resort to avoiding the artifacts by simply comparing EEG in pre and post stimulation conditions. However, so far a few methods have been proposed so far to remove the artifacts. And the most commonly used method to remove this artifact is called artifact template subtraction. So in the method, on artifact template is created by averaging several adjacent time windows, and then this mean template is subtracted from the raw EEG signal. This approach usually does not completely remove the artifacts, and therefore additional step is usually taken to separate any remaining artifacts from brain activity using PCA or ICA. the downside of this algorithm is that the method fails in removing artifacts when there are significant phase shifts and amplitude changes between time windows. And in addition, if a neural response of interest is phase locked to the stimulation, this will tend to be removed as well. So to mitigate the issue, our group used joint blind source separation techniques to separate artifacts from brain signals. So with PCA and ICA, we decompose single data set into individual latent components. For joint blind source separation techniques, they are different from PCA and ICA in that they jointly analyze multiple data sets and identify source components that are maximally correlated across data sets, yet constrained to be uncorrelated or maximally independent within each data set. So for brain stimulation experiments, most stimuli are periodic. We use either pure sinusoid or multi-size. So this fact enables us to segment the EEG data into multiple epochs and then apply this joint blind source separation approach. So using the technique, stimulation artifacts would come out as one of the source components that are dependent across multiple data sets. And our group also has proposed a new method called QIVA, which regresses out the stimulation signal and its quadrature component first, and then applies IVA to the residual. So in the next slide, I'm going to show you the denoising performance of 5 different methods, and then how we evaluated and compare their performance. So we recorded EEG from 13 healthy subjects with the following protocol. We delivered GBS for 60 seconds with 5 seconds on and 5 seconds off, and repeated 6 times. We then applied conventional pre-processing steps such as bandpass filtering, re-referencing, and eye blink removal. And then on the pre-processed data, we tried the 5 denoising methods that I showed you previously. And it's important to mention what stimulus we used for GBS. We used multi-sign signals composed of multiple sinusoids at the frequencies of interest. So to be more specific, we created multi-sign stimuli that are precisely bounded in a specific frequency band. And then we further applied a clipping algorithm to make the stimuli have relatively flat amplitude, which is advantageous for subjects' comfort to stimulation. So this artifact reduction study, we used EEG data recorded during multi-sign stimulation in 4 to 8 Hertz frequency band. And we evaluated the denoising method in 2 different ways. So the first way was to conduct a simulation study where we created simulation data sets using the EEG recorded from the 13 subjects. So here in the right figure shows how we generated the simulation data set. So in the first panel A, we have the stimulus signal as the input and the actual stimulation artifacts recorded in the EEG as output. And as I mentioned previously, these 2 signals are not identical. They are slightly different in phases and amplitudes and the shape. So the transformation from the input to the output can be modeled using the second order transfer function according to the study that I cited on the left. And we can get the parameters A0A1, B0, B1 of the transfer function. And the panel B describes the step where we added a small amount of noises to the parameters to create simulated artifacts that are slightly different from each other, just like the artifacts recorded in EEG. In panel C, we added simulated artifacts to the EEG data recorded without stimulation, and then created the final EEG data. So this simulation study has several advantages, and the most important advantage is that we know the ground truth of the data. So in other words, we know exactly what the EEG should be like after removing the artifacts with the denoising method. Therefore, we can quantify how good the denoising method is by comparing the ground truth EEG and denoised data. And we also conducted a real data study where we compared the denoised EEG data with immediate post-stimulation EEG data, and comparing differences in the power spectrum. So here are some of the results from the simulation study. I plotted the latent components extracted from the different denoising methods. And as you can see, the artifacts come out as the first and second components. And here are the plots that show the cleaned EEG data using different denoising methods on the top. And the first noticeable thing is that the cleaned EEG data using PCA look very different from the rest. And if I zoom into just 2 channels and display the cleaned EEG as red color and the ground truth as black, and we can see that PCA and ICA give poor and inconsistent results, whereas the other 3 methods seem to give more robust and improved rejection results. So the plots here show the quantitative comparisons of the different methods. As you can see, the mean square error and correlation coefficients are much better for the MCCI, IVA, and QIVA method. And if we look at these 3 methods more closely, we can see that QIVA outperforms the other 2 methods. And the next plot compares the ground truth power spectra in black color, and the color lines represent the cleaned EEG data. And we can see that at the bottom 3, they are pretty much close to the ground truth. Here are the results from the real data, where we compare the clean EEG with immediate post-stimulation EEG. So here, the black dotted line in each panel represent the pre-stimulation, and then black solid line is immediate post data. And we can see that the clean EEG are pretty similar to the immediate post. And if we computed the band power differences between the cleaned and then immediate post, we can see that QIVA performed the best. And here's another example where we asked a subject to close eyes, to open the eyes and then close, and then you can see the alpha power becomes strong during eye closure. And if you look at the left side, during stimulation, we cannot observe this. Like there is no, because the artifact is so strong, we cannot differentiate this. But after we clean the data with QIVA, you can clearly see that the alpha power increases during eye closure. How much time do I have?
I guess around 5 minutes if you want to have some time for Q&A.
Yeah, thank you. I will just quickly go through to just show you extra about the GBS effects that we found, which was interesting. So we conducted a motor task with GBS, and then we recorded EEG simultaneously from PD subjects. And so what we found was that in this study, we actually applied high frequency multi-signs in the 100 to 150 hertz range. And what we found was that during movement, before movements, so during motor preparation period, we found that the beta desynchronization becomes more prominent during stimulation, which was highly correlated with a better behavior performance. And this is the time plot of the beta power. So here the dotted line is the during sham, and then the solid line is during GBS. And you can see that the beta desynchronization becomes more prominent, and we found that it's related to the better performance in the motor task. Yeah, so with that, I'd like to thank you enormously to my supervisor, Dr. Martin McEwen, and also fundings from the Mother's Head Foundation. And thank you.
Wonderful.
Great. Thank you, Dr. Lee. Now Zeinab's gonna
okay, Ivan is asking why after decomposition PCA you see two artifact component, not one?
We found that one is the stimulation artifact, and the other one is actually 180 shifted component.
Okay, perfect. We have another question. I muted you. If you want to ask the question yourself personally, you can do that. Okay, go ahead.
So I think in the real data set, if you compare the power difference, the GVS might enhance the neural activity. I'm wondering whether the post-stimulation EEG data will be somewhat a little different from the EEG during GVS.
Yes, absolutely. I think they are slightly different. So in the result, they look slightly different as well. But the thing is, with the real EEG data, we don't know the ground truth, and we are not like 100% sure whether or not they will be the same or different. But yeah, I agree with you that they, like during stimulation, immediate pose might be slightly different.
Okay,
perfect. Thank you, Daniel. I think I muted you. Let me see. Okay, can you go ahead?
Can you hear me?
Yes, perfectly.
You were talking about the distance between the stimulation electrode and the EEG electrode, but there are some holders that can accommodate both the AT to DCS, for instance, and the EEG electrode at the same spot. You know, like in the G1020 system. And what about that? Because we cannot limit the distance between them to 8 millimeters or centimeters. I don't know the distance that you said here. Yeah, millimeter.
Okay, so the question is not from the speaker, right? It's related to Nigel's talk. Am I right?
Yeah. In general.
Yeah, in general, I mean, we are limited to the CAP or EEG system that you have. So of course you cannot sometimes control the distance between the electrode locations, if I got your questions right. Right, the question was the HD EEG cap has this predefined location that you cannot change it. So you cannot stick to like the specific distance between the two electrodes, right?
Yes, I personally don't have experience using the device, but as far as I know, I know they like stimulation and recording cannot be done simultaneously. I mean, at the same spot. That's
yeah, but the question I guess is between the is about the distance of the stimulating electrode and the closest recording electrode to that. So yeah, that is a limitation that sometimes the CAP puts on us, so we cannot control it.
Yes.
Yeah, there are a couple groups who have carbon rubber electrodes, and they do sometimes cut holes in them and place the recording electrodes. So some people have gotten around that issue by working it that way. And some groups actually are working on combining them, so it's stuff in the works. I actually have a question for you, Dr. Lee. When you were doing the repeated galvanic stimulation, did you see any accumulation of voltage over the repeats appear in your data?
No, I didn't observe that, but I like for this study we stimulated for only like 1 minute, so at least during that period I didn't observe any accumulation.
Okay, perfect. Thank you again, Dr. Lee. I'm going to clap on behalf of everyone. Great talk.
Thank you.
So the next speaker that we're going to have is Dr. Alex Casson from the University of Manchester. And Dr. Casson is going to talk to us about brain state dependent stimulation and removing artifacts with TACS. So welcome, Dr. Casson. Take it away.
Right, well, firstly, thank you very much for the invitation and for joining us wherever you are in the world, getting a bit late here in Europe now. So the towards in the title is very much a towards, and in order to do brain state dependent stimulation, we've got to get rid of the stimulation artifact, which we've already had 2 really great talks about characterizing some of that artifact and giving us some initial techniques to remove it. If I go back to one of the questions that the first speaker had, it was kind of how to deal with the artifact. And what I'd hope to kind of convince you in this presentation is that at a growth level, dealing with that artifact is pretty easy. We can apply several different signal processing techniques and get some neural data as a result. And actually, the challenge is less the hardcore signal processing, which there's lots of different things you can do. It's more about the validation and verification and how do you convince people that you've actually done this. And then, of course, that's at the growth level. When you get to the residual artifact level and some of the kind of second order effects, the physiological artifact of the nonlinear effects, actually is really tough. And indeed, I think the next speaker is going to be speaking specifically about residual artifacts. So yeah, in my lab, we do several different forms of neuromodulation, all of which we're trying to move towards a closed loop application. And for us, that means doing simultaneous EEG monitoring. And we're interested in EEG. Basically, it's our background. That's what we've always done as a lab. But in principle, it's relatively cheap and easily available compared to fMRI-based closing the loop simultaneous brain monitoring. We've also got an eye on ultimately, you know, if these kind of brain stimulation techniques have potential as out of a lab therapeutic benefits, you know, we better do them out of a lab, which you can do in principle with EEG. That brings its own challenges. But of course, it's also then got a very high time resolution, and you can see the data in real time. Sorry, my cat is here as well, which enables that kind of closed loop application. And then just thirdly, EEG is kind of the natural complement to TES because it's one's dealing with voltages, one's dealing with currents, and they're kind of different sides of the same coin. So we've probably heard most of this stuff already, I think. in terms of why are we interested in doing artifact removal. So my lab has always looked at transcranial AC current stimulation. So here we principally get a sinusoidal component. And there's two key reasons why we want to be able to get rid of this component. The first, and we heard about this in the last presentation, is because we want to see what the brain's doing while you're stimulating it. A lot of analogies today will look at the what the brain is doing before you stimulate it, what is it doing afterwards, and we want to be able to connect the dots between those and learn a lot about what's actually going on, and hopefully explain some of the difficulty of replicating findings and the high variability that we get between different studies, between different people. And so for that, we've got to get rid of this artifact. And then when we've got our eye on is closed loop modulation. So here we're taking the EEG data, we're removing the artifact, and then we're changing in some form the stimulation that we provide based upon the underlying brain state. And so the idea is that the stimulation will be state dependent, it'll be time varying, and it's really you know, an aspect of personalized medicine, right? We're looking to individualize what we do. It's not everybody gets 10 hertz taps at 1 milliamp. It depends on you and your data right now. And of course, there's lots of hypotheses out there that, you know, this kind of stimulation could potentially be more effective, and it might provide reduced variability, again, between different studies, between different people, taking account of somebody's brain when you're actually doing the stimulation. So in terms of the specs that we have for doing artifact removal, well, if we're going to enable the closed loop aspect, we've got to be able to do it in real time. And so very computational complex techniques aren't valid. They are if you're just doing the offline first case, that would be okay. We also need them to be training free. So there's some papers out there that look at collecting a whole load of EEG plus artifact data. You learn the shape of the artifacts, the typical transfer function that you get, and then you can use that to remove the artifact. But that's not amenable to closed loop paradigms, because every time you change the simulation, you've got to change your training, you've got to redo that step. We're also very keen, not necessarily essential, but we're very keen to be channel count independent, because again, we've got our eye on, if we're going to do this out of a lab potentially in X many years time, we don't want to have to set up 256 electrodes to be able to do that. We want to be able to do it with a minimal montage that can be done fairly quickly, and all of that sort of stuff. And then lastly, and almost certainly most importantly, well verified. It's very difficult to convince people that once you've applied all manner of signal processing, you've actually got true EEG data. So we've already had a great talk about characterizing the stimulation artifact. This is kind of my take on that, particularly for tax. And so we don't have the device on artifact here. That's a new one to me actually. But we do have the filter step response when we turn the stimulation on. You won't see that if you do a ramp up, of course, in your stimulation, but you will see it when you start to close the loop on your stimulation and you start introducing step changes in the stimulation that you're providing. Broadly, we then get a sinusoidal stimulation, of course, almost certainly overlapping with our cortical frequencies of interest, as we heard about in the last talk, which means you can't do very basic signal processing, just ban NOx filters to get rid of the artifact. We estimate the signal to noise ratio at about -40 dB. There's different ways in which you can quantify that. In terms of the signal processing literature, that's pretty low. GPS, very different application. It goes down to about -105 dB, and you can recover the signal. Kind of PPG, so smartwatch motion artifact removal, which has been a big success story in recent years. The artifacts are about -20 dB. So a lot easier than we're dealing with here. And then we get into a lot more detailed kind of artifacts. So we see about 100 microvolts ripple on top of the stimulation that we do, coming from all manner of different sources. Principally, we think because the stimulator isn't an ideal current source, but also it's constantly trying to drive the same current through mildly changing impedances as you move about, as the electrode drives, all of that sort of stuff. And so you've got another kind of you've got something fighting against you almost. It's trying to adjust itself in order to maintain a fixed average current level, and that introduces some noise. Now, what I'm not going to talk about particularly in this presentation is physiological artifacts. When we collected a lot of the data for our EEG plus TACS work, actually that wasn't really on our radar. And so we don't have simultaneous ECG at the same time where we can pull that out explicitly. But if you just look at this ripple, you can see a near perfect heartbeat coming out. It looks like an ECG complex and a QRS complex. So it's there, and we'll talk about some of the residual artifacts a little bit later on. One of the other questions was talking about kind of where to place electrodes and that sort of thing. And I just a slight comment on that. This slide was in here anyway. What we find is that the EEG artifact, it depends on your stimulation amplitude, obviously, but it's in the millivolts range. Okay. Now, of course, if you do a simple sum, the stimulator is putting in about 10 volts, so an awful lot more than that. And so you don't see that on the head because of the common mode rejection ratio of the EEG amplifier. So your typical EEG amplifier is designed to not record 50 hertz, 60 hertz mains noise. It rejects that because you get the same signal appearing on all of the electrodes. It's common for all of them. And so it attenuates it, typically by at least 80 dB, and probably a lot higher for a modern amplifier. Of course, a EEG amplifier, it will depend a lot on your model, but they typically have kind of 10 millivolts, maybe up to 1 volt if you've got a very high-end model of input range. Okay, so anything above 10 millivolts, 500 millivolts, whatever your amplifier accepts, will start to saturate. And so you've got to rely on a lot of your artifact being common across your electrodes in order for it to stay in the input range of your amplifier. And so in terms of how far apart should electrodes be, where should you be placing them? What you want is a balanced setup. You want your reference to be in the middle, so you maximize the common components of the artifact that you see across everything. And so of course the electrodes are very close to where you're putting in the currents. Actually, maybe the bottom left circle there, so really be on the bottom right, maybe. But the electrodes are very close to your electrodes, they're likely to saturate, just because they're really close to the stimulation site. But equally, the ones which are far away from the reference are more likely to saturate, because they're going to see a different common mode component compared to the other ones. And so you can improve your chance of not saturating the amplifier by putting the reference in the middle. And if you're really saturating, you move to bipolar chains. And I appreciate I've not drawn this as a chain. You probably would have it as a chain, but you can move to a bipolar montage. So you get two EEG electrodes very close together, and they'll see a very common artifact. A lot of that will be suppressed at the hardware acquisition stage. So in terms of artifact removal methods, we've looked at two. So we've got the template subtractor method, which was referred to in the last presentation. We call it SMA. And that SMA is actually implemented in the toolbox, which wasn't made by me, but you can download for free if you wanted to look at different implementations. And Robert, who I think is on the Skype, made that. And there's lots of other signal processing functions you can investigate in there if you wanted to. And then what we also looked at were adaptive filters. So I won't go through the maths too much. It's in the paper if you particularly want to look at it. But this is a template subtraction method. So you look at a small window of data, use that to build an artifact template, and then subtract it off. For the adaptive filter, well, this is essentially saying it's a parametric situation. We're doing this. We know what the artifact is. And it's a bit like, you know, my noise cancelling headphones. So we measure the tax that we put in. Some tax hardware will let you do this. They've got a signal out, so they will tell you what the actual output is. So we record that at the same time as the EEG, and then we can use that to remove the artifact that we get. Now, of course, what we get is one estimate of the tax artifact. And as we've already heard, we don't get exactly the same artifact at all of the different electrodes. And so there's limitation to this approach, but it is one that we've looked at. So, as I say, those two bits, as I say, the maths are in the papers, are probably the easy step. The more difficult step is the verification, because of course, when we're doing this on a person, we don't know what the EEG is actually doing. It's not like the ECG, where you have a lovely known waveform. You could tell very easily if that was working or not. And so we would go back to our more clinical ties and say, you know, it's not about any one bit of information, right? There's no one test that you're going to be able to do and say, look, this is working. It's about doing lots and building up an overall picture and weight of evidence, you know, and what's the most likely thing that's going on, rather than one killer test. What I'm going to go over here are 5 different methods that we've looked at. We're aware this is a review we published late last year of 9 different methods which have been looked at so far for validation in the literature. What my lab doesn't do is any numerical simulation. So we don't have any of the computational models like in the first talk, or the kind of circuit models as in the second talk. We're a bit more practical than that. Because what we have instead is a head phantom. So this is ballistics grade gelatin. We've characterized this for how did it reflect the electrical properties of the head, and it depends on how many cortical layers you want to model, but it's surprisingly good from that Rankin cell type model which we saw in the previous presentation. And so what we have in here are some internal electrodes which lets us play in signals, and then we can do tax to the head at the same time and do EEG measurements from it at the same time. Now, of course, there's limitations. There's no hair. It's dead easy to connect electrodes to this. You get no impedance issues. We only have 2 sources inside the head. There are people who have head phantoms with 16 sources. We also don't have any physiological artifacts, no heartbeats and so on. But it means that we know what the correct EEG signal is, and we're doing this in practice, so we can do all of our closed loop test development on this sort of setup. And so these are the kind of headline results. So this is just essentially some arbitrary EEG data stimulated at different frequencies, all at 1 milliamp, and looking at the input and the reconstructed data after artifact removal, using both SMA, so template subtraction, and the adaptive filter, and they're pretty good. We see a drop-off in performance at higher frequencies, and we'll see that pretty consistently. And of course, we're doing this on our phantom, so we can probe a bit more in depth than that, and particularly to look at start and end artifacts, because any filter has a memory associated with it. Our template has a memory associated with it, and so we can play around to trade off the performance on this slide, you know, the SNR, versus the transient type artifacts that we introduce. They're coming from the artifact removal process, and how quickly we want to be able to get an artifact-free trace. So if we then move to on-person data, so this is the second method of testing. Firstly, we did a very simple, again, like in the last presentation, an eyes open, an eyes closed task, because this gives, in EEG terms, a lovely big signal that we know is going to be there, and we can just have a look, essentially. And so the SAM is a recording with no tax applied to it. That's just EEG. Someone closed their eyes. For the other three, these were done at a different time. So this is EEG and tax, and we've done the artifact removal. So we don't expect these to look exactly the same. Okay, they're different actual recordings. For SMA, we can see some alpha bursts coming in at about 31 seconds after the person's closed their eyes. And we can see that with the PCA and with the adaptive filtering as well, if a bit less clearly. And on this slide again, what kind of big signals can we look for in the EEG? Well, it's eye blinks. And the top part is showing the recorded signal, and then the artifact that we have removed at each point in time using the different methods. And then we can see eye blinks coming out. Again, they're lovely, nice and big things. That's not the end of the on-person testing. Then look in the frequency domain, and firstly, you see the very classic, you close your eyes, you get a big alpha peak coming in. That pops out no matter what stimulation frequency we're looking at. So we can be stimulating at 10 Hertz, so right in the alpha band. We don't see that peak when the eyes are open, and we do see that peak coming in when the eyes are closed. Now, we also see an awful lot of 40 Hertz interference when we're stimulating at 40 Hertz. Yeah, we are not doing a good job at that upper frequency end with either of the methods, and I'll say a few words about that in a few slides time. So that was the second part of testing, which is really just kind of having a look at the data, right? The next step was to look at descriptive statistics. So we looked at 4, and just looking at, are there any statistical changes in our EEG between the sound data and the clean data? And of course, we've got loads of sound data. And the answer is no, there's not. So from that descriptive stats point of view, we're seeing the same thing. The next step was to say, okay, well, we don't know the kind of the structure of the EEG at any one point in time, but we can do some evoked response type measurements. And so what we did here was an N170 task. So we showed a recognizable face or a non-face, and in trials where there's a face, we expect there to be an N170 and possibly an N400 as well. And we can recognize that evoked response during stimulation. So here we're doing it at 40 Hertz with 250 microamps of stim. Now, particularly for the adaptive filter, we see a lot of 40 Hertz ripple in there, and that's what we saw in the frequency domain a couple of slides ago. And there's a number of causes of this. So we kind of feel more than anything that actually the stimulator is never an ideal stimulator, it's never an ideal current source, but it gets a bit less ideal as you move up in frequency. Actually, a bigger issue is we're just not sampling the EEG fast enough. So we're sampling at 500 Hertz, and actually you're really decreasing your phase margin, essentially, as you push up that, as you push up the stim frequency compared to the sampling frequency. But 500 Hertz is the highest we can go to. And then with the adaptive filter, as we said, we're only getting one estimate of the artifact to remove, and we know there are differences between what you actually see on each channel. And then lastly, what we did was to put some machine learning on this. And so what we did here was 5 Hertz tax and 2 different working memory tasks. So we got people to do an NBAC during stimulation and to do a backwards digit recall task during stimulation. And the idea here is that these will be very similar, kind of working memory type tasks, but also distinctly different tasks. And then we split the data into just baseline resting data, and then EEG during the task, EEG during the task when you're stimulating, and then EEG when you're stimulating for that baseline. And what we see is that if we split into 4 classes, so comparing baseline compared to baseline plus stim, task compared to task plus stim, we can separate those classes with a pretty good accuracy. And we kind of expect that, right? So doing a working memory task gives you different EEG compared to baseline. And of course, when you stimulate, you can separate that out, because this is after cleaning, right? If there's loads and loads of residual artifacts left, they'd pop out, right? It'll be dead easy to recognize loads of artifacts and classify them as a different thing. But then what we actually see is we can also separate out the 2 tasks during stimulation. So we can, the classic can classify and identify with a good level of accuracy. Were they doing the end-back task, or were they doing the digit recall task during the stimulation? And what that means is that for the classification process, the residual artifacts that are present don't dominate what it's using to make its decision. And so what we're getting is data that varies with the task that's present. And so either we're getting EEG that's varying between our different tasks, which is what we would expect, or we're getting artifacts, residual artifacts that are varying between our tasks. And with all of these things, we can't rule that out, but we don't see why the stimulator would be giving us different artifacts for the different tasks. We're not changing the EEG setup or the stimulator or anything there at all. We don't see physiologically why we'd be getting different artifacts for switching tasks. Again, persons sitting at the same computer, very minor difference in terms of the actual EEG task that they've been given. And
Alex,
so,
sorry to interrupt, just you have 2 more minutes left.
2 more minutes, okay.
Yeah.
And so just to kind of overview our current status from my point of view, is EEG data during STIM as good as normal EEG data? No. And it's never going to be, right? We're doing something really disruptive to the EEG here. We've always going to have to treat it with some gloves on, with more careful experimental protocols and all that sort of thing. Are there residual artifacts present? Yes, right? We see that particularly at 40 Hertz. Does it matter? Well, this is where it's really over to you guys rather than me as the engineer, because clearly, certainly in my head, we can see physiological components. We can get some valid EEG during this. Are you able to use that for your experiments? That depends on exactly what you need to see and the robustness of your experimental protocol. And is it good enough to start making use of? Yes, it is. And we need that because we need to start getting feedback on how well it works in order to improve it and do it further. And in terms of the next step, we can now do the artifact removal to the level I was talking about. We can do that in real time, and we've got the technology, but not the funding bits in place for doing that closed loop based stimulation, certainly at the max frequency, at the max phase level. And that's all I wanted to go over. Thank you very much.
Thank you, Dr. Kaslan. So now we're going to take a couple questions and then move on quickly. I think we'll probably take about 1 question, and you can pour in more questions in the chat.
Yeah, in the interest of the time, I think the next speaker can go ahead and share the screen. Meanwhile, we can, I'm going to unmute you, Sarah. Could you please go ahead and ask your question?
I don't know if you guys can hear me.
Yes.
Yeah.
Perfect. Okay, so first of all, this is fascinating. So really congrats for this. And was just wondering, do we need particular amplifiers other than a montage to do so? And your software can work on MATLAB. So like if realistically I can just, start tomorrow and try it out, or how does it work? Thank you.
So I wouldn't want to guarantee for every amplifier. We've used quite a few different ones. I think if you get the montages correct, I think you could probably get it to work with pretty much all, to be honest. I don't think I'd be too concerned, but you would need some care and experimentation. In terms of MATLAB, it is working in MATLAB with some buts. I cut this from my presentation. It's not as easy to share as we would have hoped. We did have aspirations to make this all open source, so on and so on. For various reasons, we're not based upon lab streaming layer. And so we need drivers for every EEG device that we use to get it into our system. And that's a real support headache. And then equally, we need drivers for every tax source that we use. And so actually, sharing the code is easy, but it would only actually work if you're using the exact same hardware arrangement as we are. And fixing that is harder than we were hoping for.
Right, thank you. So you guys can keep your questions coming in. We can answer those at the end. Next up, we have Dr. Florian Kasten from Karl von Ossietzky University in Oldenburg, Germany, who's going to be talking to us about analyzing EEG and MEG signals in the presence of residual TACS artifacts. So welcome, Dr. Kasten.
Yeah, thank you very much. I hope you can all hear me and see the slides already.
You're all set.
Okay, great. So essentially the talk is going to be kind of a continuation of what we just heard. I will not that much focus on how to remove the artifact, but rather on what we can actually do with the results of these artifact removal methods. We've already established all these problems that we have with artifact removal. TACS causes huge artifacts that heavily disrupt our EEG and also our MEG signals. And although we have quite some different approaches that have been suggested in the past couple of years, none of these methods so far can provide perfect artifact removal. And that's due to the complicated nature of the artifact. There are different processes that can modulate the amplitude of the artifact, which in a nonlinear manner, which makes it extremely hard to clean off. And in TACS, we especially have the problem that the artifact overlaps with the brain signal we're interested in, and actually also looks very similar to what we're actually looking for. So a residual artifact that remains in the data will naturally have an increase in amplitude, which we would expect the stimulation to cause in the brain. We have high phase coupling between the artifact and our waveform because it's the stimulation waveform, because it is essentially the stimulation waveform. And so it's very difficult to disentangle stimulation effects from artifacts, especially assuming that stimulation is actually doing the thing that we're hoping that it can do. And also in several of the previous speakers have pointed that out, we don't know the ground truth underlying signal, and it's very hard to get into methods that can actually give us access to that. So even if we would, for some reason, stumble upon a perfect method, it would actually still be very hard to without a doubt, prove that this method works perfectly. And I brought one example that I encountered during the last years. It has been suggested some time ago that one solution to overcome the TACS artifact would actually be to, instead of just stimulating with the sinusoid, use a high frequency carrier signal and modulate that in amplitude with the frequency that you want to target. And if you look at the spectrum of such signals, that would shift the artifact into higher frequency regions and avoids artifacts in these lower frequencies, so that we avoid the overlap between the artifact and the brain signal we're interested in. And recently, a colleague from North Carolina in Flavio Fröhlich's lab simulated that together with us, and he was able to show that in neural network, this type of stimulation actually creates similar entrainment effects as conventional TACS, although admittedly you have to crank up the intensity quite a bit. So from a theoretical point of view, this looks very promising and seems a very elegant and beautiful approach to solve the artifact issue until you look into your actual recordings. Because when we then record brain signals from this is in case my brain activity in black, you can see my natural power spectrum in the MEG. This would be my alpha peak in black here, and in the colored line depict what we see when we actually turn off this type of stimulation with 10 Hertz and 23 Hertz amplitude modulation, and we get pretty strong peaks at the frequency of this modulation, and this is a logarithmic scale. So these artifact peaks here are about 500 to 700 times larger than my intrinsic alpha oscillation. So this cannot be some kind of strong entrainment effect. This is unrealistic. We also see that the topographies are very strongly distorted. So this is a technical artifact. We later found out that this is due to nonlinearities of the hardware. If you're interested in the details, you can check out this publication. But it's just to illustrate how even a very straightforward and beautiful approach in theory can terribly fail in practice, because you may overlook certain things, and how difficult it actually is to get into to get to really clean online TACS data. So giving this kind of frustrating experiences that probably everyone who tried these methods has made, you could argue that maybe just trash all these methods and spend our time with something more enjoyable. But on the other hand, I think there's also a lot that we can gain if we manage to get insights. If we want to understand how TACS works, we have to get insights into the brain signals and how these are changed by the stimulation. We want to understand how the stimulation changes behavior. We need access to what is happening to the underlying brain activity patterns during stimulation. And so also pointed out before, this may also allow to further optimize stimulation approaches and increase effect sizes, which would be very desirable for clinical applications and help many people. So what can we do now with that? What we've also seen in the previous talks, the removal might not be perfect, but it still might be good enough under certain circumstances. And one thing that could happen or seems very promising is that these residual artifacts that we have in the data may just cancel out if we contrast two conditions during stimulation. The previous presenters have shown that they contrasted eyes open, eyes closed data, for example. Another thing you could look at are event-related oscillations. This is something that we did some time ago. We asked participants to perform a mental rotation task. This kind of task is well known to cause a strong suppression in the alpha range after stimulus onset. So as soon as you start mentally rotating an object, alpha amplitude goes down over posterior sensors. During that, we applied TACS. We had a baseline period without stimulation, and afterwards we also did some post-stimulation measurements. We stimulated in the alpha band with posterior montage, and then we applied a linearly constrained minimum variance beamformer, which is another approach to get rid of or strongly suppress the artifact, but that is also known to not work perfectly. And then we had a look at the power difference between these pre and post stimulus interval, and we implemented some control analysis to try and rule out that our effects could be explained by a TACS artifact. So we looked into power differences. One thing that we realized at some point is that it's very crucial how you do that. Traditionally, if you look into event-related oscillations, you often calculate something like this event-related desynchronization, which is essentially a relative measure to characterize how the power of the oscillation changes. So R would be the power pre-stimulus, A would be the power post-stimulus, and then you divide that by the pre-stimulus, and then you have the relative change. If you now apply TACS, you could say, okay, power in these periods is actually a combination of the brain signal that's underlying or that participants are showing, and an artifact that we artificially impose on these signals, and then rewrite the formula. And you quickly see that this measure will be would be strongly biased by a residual artifact, because it cancels out here and it remains here, and this may strongly affect your results. So for this study, we decided to instead of doing this, we decided to go for the absolute difference, where we would hope that under the assumption that in both periods the artifact is approximately the same, these would cancel out and give us more robust results. To illustrate how important this can be, we also recently did a little simulation. It's not very sophisticated. You essentially would just created some random values for the pre and post stimulus power that give us value pairs that we can use to compute ERD values and power difference values that give us a ground truth, which you can see in blue here. And then according to these formulas I just showed you, we can also add an artifact. What you see here is an artifact that would be approximately 3 times the size of what we set for the pre-stimulus power. And we allowed it to vary by 10% between pre and post stimulus to incorporate random fluctuations due to heartbeat or whatever processes you may have. And if you add these kinds of artifacts and then recompute the measures, you can see the relative change measure is actually very strongly biased. You get a significant difference. These are the same underlying values. It's just an artifact added to them. And this will give you a significant effect essentially. Whereas if you compute the absolute difference, there's barely a difference between the two means, and the difference still very well resembles what we have in the ground truth data. And in order to see how the size of the artifact plays a role here, we rerun the simulation with different artifact strengths. So essentially each dot here represents such a difference for the absolute change and for the relative change. And for the absolute change in orange here, you see that fluctuates around 0, which is good because we don't want a difference here because it's the same data. And we see if the artifact gets larger, of course, these random fluctuations kick in more strongly and cause a jitter. But while for smaller artifact sizes, that still seems kind of tolerable, you can see that even for very tiny artifacts that are just fractions of the underlying brain signal, the ERD is strongly biased and will almost immediately give you systematic differences. So to sum this up in some words where you can learn from the simulation, if you would like to have a strong online effect, you should actually go for relative change. If you want an effect that's actually there, rather go for absolute difference. So we went for the latter. And if we looked at our data during the time points that we applied stimulation, we actually saw that this absolute power difference increased quite strongly relative to the baseline blocks and also to post-stimulation. So when we apply this more robust measure, we see quite a remarkable effect. Still, the question is this an online effect, or could this still be explained by an artifact? There are two important assumptions from the simulation. We saw that if we want this to work, we have to rely on that the artifact suppression removes large part of the artifact in order for this to work. And even more important, we have to make sure that there's no systematic change of the TACS artifact by the task. We have heard that physiological processes can affect the strength of the artifact. We see that during heartbeat or respiration. You could imagine a case if you present a frightening stimulus, for example, that may change body impedances, that may change the heart rate and these things, and that could so the stimulus could systematically change the artifact. And if for some reason this mental rotation task makes some people nervous, you never know. This could explain why we see such an effect. So we did two control analyses. One thing that we wanted to do is characterize the strength of the artifact. And many studies actually rely on visual inspection to check if there's still artifacts in the data. We wanted to have something that you can try to use more objectively. So we computed the ratio between the power that we observe during TACS, which should essentially be some sort of mixture between the brain activity that we have in there and the artifact that we impose on that. And we can compare that to the power that we observe when stimulation is switched off as a reference for what we observe as natural brain activity in our participants. This can, of course, not prove if the data is artifact free, but what it can do is give us some sort of upper boundary for how strongly we suppress the artifact. So if brain activity plus artifact is still 100 or 1,000 times larger than the brain signal, we may have a problem. In our case, we were down to, in some hotspots, to a ratio of 1 to 10. I think the worst voxel in the whole study was about 1 to 100 in a single voxel. But on average, in these posterior regions that we actually were interested in our analysis, we're down to something about 2 times or 3 times the brain signal. And still, this is a mixture. This could, of course, also reflect stimulation effect. So it's still we're already in a range where it's not unplausible that this could also be an effect on the brain oscillations itself. You sometimes see if people close their eyes, alpha amplitude goes up quite dramatically. The other nice thing about this measure is that we can actually plot topography. So what you also can see are these hotspots, and they actually quite nicely resemble the position of the central electrode and the locations of the cables. The other thing that we had to make sure is that there's no systematic modulation of the artifact. What we did there was that we looked at the sensor level signal and extracted the envelope in the alpha band. If we don't apply stimulation, this should essentially reflect the dynamics in the alpha band. Whereas if we apply stimulation, the dynamic that we see in the envelope should be dominated by what is happening to the artifact. What we can then do is segment around the events and see if there is a dynamic change in the envelope of the artifact, and correlate that with the effect that we saw on the source level after we suppressed our TACS artifact. And so we did these correlations separately for the 2 sensor types that we have here in our MEG. What we do see is that if we don't apply stimulation, so that's this sham condition, we have a nice correlation that we should have the sensor level data reflect the source level data. But during stimulation, there's actually no correlation between the envelope change and the change on the source level, which was reassuring for us that the modulation of the artifact is not driving the effect that we see on the source level. So this was reassuring for us that we're actually seeing an effect of the stimulation and not of the artifact. So to summarize a bit what you can take home, hopefully, one thing is artifact suppression is powerful, but we have to keep in mind that it's imperfect. And maybe even if it was, maybe we can't even prove that. Based on this assumption, we should expect residual artifacts to be in our data and expect to need to account for that. And if we embrace this fact, we can incorporate that into our experimental designs, into our analysis strategies, and we can think and come up with control conditions to rule out and try to disentangle stimulation effects from the artifact. Based on what you saw in the in this little simulation, I hope this will motivate you to very rigorously check if your outcome measure that you're looking at can be biased by the influence of an artifact. As you've seen, some can be very vulnerable and other might be very robust. And I personally also think it should be good practice to report the size of the residual artifact and to give people an intuition if what you're doing in the subsequent analysis is actually possible, or if the artifact suppression did work out in a way that this is not reasonably possible. And you should try to implement and come up with reasonable control analysis to try and disentangle effects of artifact and stimulation. The other thing is canceling or contrasting conditions, of course, is a standard analysis procedure, just as people very often do source analysis. So these rather standard analysis procedures can have artifact suppression capabilities. As I've shown you, these can be very powerful to uncover effects, but it's also very important to keep in mind that they can obscure your artifacts. So if you want to implement a new method and then say, okay, and I now evaluate the method by showing that I can recover source reconstructed event-related brain dynamics, you actually apply two hidden or implicit layers of artifact suppression, and this result down here may look good, but it may not tell too much about your primary method. And so I think it's very important to try and it's fine to do this to show that it has a practical use, but I think it's still important to show data at this step to don't give people unrealistic expectations about your methods. To summarize that, I think with careful, if we can come up with careful designs and analysis, we can actually already, with the methods at hand, get very interesting insights to stimulation effects. And with that, I would like to make a blatant advertisement to a research topic or special issue that we're currently putting together on multimodal approaches to non-invasive brain stimulation. So if you're into these kinds of things, you're combining brain stimulation and neuroimaging, feel free to check it out. And if you like to contribute, feel free to get in touch with me, drop me an email or tweet at me. And these are the lovely people I'm working with. Thank you.
It was a great talk, Florian. Thank you so much.
So now we're going to take a couple of questions.
Yeah, so let
chat.
me get to the questions. There is this question. Do you see harmonics or subharmonics of the TACS artifact in your EEG paraspectrum?
I'm mostly looking at it in the MEG. We definitely have a lot of harmonic peaks in the MEG during normal TACS and also during amplitude modulated TACS. Yeah.
Okay. There is another person. I don't know what's the name. iPhone. I unmuted you. You can ask your question directly. Apparently, he's interested in amplitude modulated stimulation that you suggested earlier.
Yes. Yeah. My question pertains to the amplitude modulation, high frequency carrier type stimulation that you talked about toward the beginning of your talk, and why you wouldn't just try to use a low pass filter very early in stages going from electrodes to the EEG amplifier, so that you never had to deal with nonlinearities induced or introduced by later stages.
We tried that. The problem is that unfortunately that doesn't solve the problem. It's not just non-linear. So essentially you cannot really, none of the hardware that we're using is perfectly linear. It's pretty good for the purposes they're made for, and that's measuring tiny signals coming from the brain. But we're putting, and for that the non-linearities in the systems doesn't matter. And but as soon as we pump in such a huge artifact signal, and that is modulated in a non-linear way, you create these huge artifacts. And the problem is, the problem is, it's not just the stimulator, but it's also the recording device. So even if you are able to get in a perfect amplitude modulated signal, the measurement stage will distort that.
Right, but what I'm asking is, rather than trying to digitally filter it out with a low-pass filter in the end, why not low-pass filter it by analog means on the way into the amplifier. So you don't have to ever deal with nonlinearities of the amplifier.
But then you filter out the brain signal.
Not if you're dealing with low pass filtering. If you're dealing with kilohertz carrier frequency and you're low pass filtering everything below one, let's say 1 kilohertz, your brain signal is all there.
Yeah, I have to think about that.
I think in the interest of time, we'll move on to the next speaker. You guys can definitely continue the discussion in the chat window. Thank you. And so next up, we're going to have Dr. Leo Tomasevic from Copenhagen University Hospital in Denmark. So welcome, Leo.
Yes.
Please take it away.
Yes. Thank you. Thank you for organizing this and to make me be part of it. So I will change a little bit the topic. I will jump from TACS and TDCS to TMS, but I will keep talking about EEG and the artifacts. I'm a research fellow at the DRCMR, which is a research center in the University of Copenhagen Hospital Gebodh. And yeah, I'm working mainly with EEG and everything related to it. So I will just give a very short introduction to EEG. Everyone knows how it works, but since you were mainly talking about EEG somehow in real-time EEG or EEG that is not, that doesn't change due to stimulations, but it's more an ongoing EEG, I will mainly talk about event-related responses in EEG. And this is how actually TMS EEG is studied, where a TMS pulse is given at certain time points and it's recorded with EEG. After many trials, we average them and we get the time evoked response, which is similar to what is the standard method when we do any kind of EEG stimulation, event stimulation protocols. The big difference here is that the TMS as such is a noisy device because it produces a big magnetic pulse that affects the EEG channels. It produces other effects that I will talk about later. But what I want to say is, why do we have the need of combining TMS and EEG? The main need was that TMS has been mainly used for studying the motor cortex by stimulating the motor, primary motor area, and then analyzing the output, which is a muscular twitch, peripheral twitch. And then the idea was what we can do if we can record the activity after the pulse on any other brain area. So it means, can we study the local excitability outside of the primary motor area? And then the other question was, can we also study what is the connectivity? It means, if I stimulate one area, can I see what is the response of the surrounding or far areas from that one, but they are physically connected. And some very nice studies have been done with TMS EEG. We'll start with the Rosanova paper. And they actually have shown that if we stimulate a specific brain region with TMS, that brain region will respond maximally in the frequency that is the natural frequency of that specific brain region. This is a very nice, in my opinion, very nice study. Another study, it's actually from almost the same group. It was not the same group at that time, but some of the authors are the same.
Leo, sorry, I
yes.
have to. I'm disturbing you, but at least on my screen, the slides are not changing. So I think you should be on slide 5, because I can see the side panel, but I'm at least seeing just the main slide. How is the organizers?
Yeah, it's
yeah,
not.
Sorry.
No, sorry.
So you don't see anything, me changing slides?
You
No,
can
I
see
think
your first slide, so you just have to move down. I think we're just seeing your extended display.
Okay.
We can see your mouse moving, so.
So this is interesting.
mhm.
What can you see now?
We see your mouse on slide 1 or 2, I believe.
Oh, but I see there was the Massimini paper.
Yeah, this
It's
was
not
the.
in,
Do you
So
see
now
this one?
it's the Massimini paper.
yeah.
Yeah, so maybe I cannot.
And it's
go-
not in a slideshow mode, so we see all
Yeah, it's
the,
not in the slideshow mode because I think that the slideshow mode it was not working probably.
I think you can just proceed this way. Just click on the slides
Okay.
on the left.
Have you seen the previous slides?
no, not.
Okay, sorry. So this was the
No,
slide about combining the two techniques. This is the slide about Rosanova paper where he stimulated different brain regions and they responded in the frequency that was the natural frequency of that brain region. And this was the Massimini paper. So I'm here now. Can you follow me?
Yes, we can see it.
Yes.
Okay. So probably the presentation mode was not working. Sorry about it. No, this is actually a very interesting paper where they have shown that with TMS EEG, they can actually see how the different connectivity of the brain is at the time of stimulation. And this is during wakefulness and sleep. And then they have shown how when you stimulate a brain region during wakefulness, the information flow spreads, and actually the curve, the ERP evoked response is very complex, while stimulating during non-REM sleep, the response is localized and it's much higher and less complex. There were also studies where it has been, for example, in this case, has been studied the effect of GABA modulating drugs. And this is just another example, but there have been many studies so far. But this was just a little introduction. I promised to speak about artifacts, and this is more or less a simplified this time description of the artifacts that appear with TMS EEG. So in the very first early stage, in the first 5 milliseconds, there is the pulse artifact, which is due to the TMS, the direct interference with the electrodes. There is the decay artifact that is due to the charge of the electrodes, and they need to discharge to get to the baseline. Then there is a very early artifacts within first 20 milliseconds, which is again the decay artifact ongoing in case it hasn't discharged yet. Then there is the muscular twitch. And then in the middle time period between 20 and 80 milliseconds, we have a bit of everything overlapped. And in the late responses, the peripheral response to the TMS is dominating. What is the peripheral response to TMS? This is the auditory stimulus of the TMS coil, which is very loud. It makes the sound depends on the stimulator using. Then there is the skin sensation, because every time we stimulate the head, we also can feel the stimulus. And then there is the sensory input caused by muscular twitch, for example, because every time we stimulate and we evoke a muscular twitch of the core of the cranial nerves, with stimulating the cranial nerves, we will also have then the sensory response in the cortex due to this stimulation. And obviously, if we are stimulating the motor area, we will have a muscular twitch of the related muscle, and this will again come back as a sensory input to the cortex. We can say that those are cortical unwanted responses. So a little bit about the pulse artifact. This is huge. It's many orders higher than the EEG response. Actually, we can record the TMS EEG only if we use a compatible EEG amplifier, because if the amplifier is not compatible, the signal will saturate and recover after many seconds, some seconds. We shouldn't use filters during acquisition because the filters will spread the pulse artifact around the pulse itself and contaminating the EEG signal. It's still not possible to deal with this artifact. What we do, we just discard it by interpolating the time points where the artifact is present, since it's usually in the first milliseconds, as I said before. What I usually suggest is to use as high sampling rate as possible, because with a high sampling rate, the artifact is much shorter, because obviously this is depending on the sampling rate needs filters, and if we use filters, we spread the artifact. In this case, well, for example, is an example of 80 kilohertz acquisition on the right, and you can see how the signal recovers much faster, mainly with the biphasic pulse. The decay artifact is an artifact that, as I said, affects the channels that need to discharge after the strong pulse. And this artifact is usually, we can deal with it if we prepare properly the EEG channel. So if the impedance between the EEG channels and the skin is properly done, the channel preparation is properly done, then this artifact is almost absent, even though there are some, it can remain a little bit more during the monophasic stimulation. I'm showing us a paper where they tried the different methods to clean it afterwards when the data were actually contaminated by the decay artifact, and all the ICA methods that they have used were leaving some spurious signal. Then we have the cranial muscle artifact. I think I will just introduce it. It's an artifact that contaminates the first 15 to 20 milliseconds. Sometimes it's much shorter. Sometimes it's just until 8 milliseconds. This depends a lot on the area of stimulation, and it depends on the intensity of the stimulation. But I think probably that Tuomas Mutanen will speak more about it and about some methods how to deal with it, post-processing methods. Then I introduced already the click auditory evoked responses that are due to the strong click of the TMS coil. This response is usually very, very prominent at around 100 milliseconds, and then it has a second very strong phase at around 180, 200 milliseconds after the pulse. And the distribution of this noise is mainly in the central electrodes, having a negative deflection. This is important because N100 is one of the components that has been mainly studied in TMS EEG protocols as probably as a component that has been presented as a possible representation of the inhibition of the brain after the pulse, but it's strongly confounded by both the auditory evoked potential and also by the skin sensory evoked potential, which is a somatosensory evoked potential, again due to the physical sensation of the click on the skin after the TMS pulse. This is an example of how it's N100, for example, when we stimulate the peripheral nerve, the median nerve, then we have the first cortical responses at 20 milliseconds, and then we have at 120, we have this again on the central electrodes, centrofrontal electrodes, negative deflection that can be seen exactly 100 milliseconds after the first cortical response. Then there was a first sham that has been done to see what would be the effect of the stimulation of the peripheral components of these unwanted signals. This, as you can see, this sham has been done by stimulating the shoulder of the participant and then comparing the effects of the stimulation of the shoulder with the real stimulation on the cortex, and there were some components that were overlapping. We have then done a more realistic sham where we have delivered the pulse over the head, but a very low intensity compared to the real stimulation and far from the head. It's not very low intensity, it's because the distance was much higher. And then we also separately, but at the same timing, have delivered us a little electrical stimulation over the scalp to mimic the skin sensation. Obviously, this was not perfectly matching the skin sensation because it's a little bit different, and we are still not able to completely mimic it, but it was a way to have a sensory response of the scalp. What we got in this experiment is that some of the real TMS curves, you can see them in the first two rows, are actually very similar to our sham condition, that is the last row. And mainly, I would highlight that N100, which is around 112 milliseconds in our case, was pretty similar, both in the shape of the responses and in the distribution of the scalp. I have to say that the only way to deal with this N100 effect that is due to maybe to the auditory evoked responses is to have a good noise masking. We didn't achieve in this study to have a perfect noise masking, and actually any time when we see this N100 P180, I would say that the noise masking was not working properly. And we are still trying to find the best solution to deal with it. With this same study, then we performed also the various correlation methods to see how much the signals were correlating, and we saw that the major part of the correlation was actually in this central, a little bit more central frontal electrodes, which are those that we have seen also as those that represent mainly the auditory and the sensory stimulation. So this study obviously made some discussion, and we were very happy that the discussion was made, because this always helps to improve. And then I also started to check what are somehow the parameters for stimulation that are shared among different labs, and which are not so shared. And I identified three different approaches in stimulating, in using TMS-EEG, which are based on where to stimulate and the intensity of stimulation. So the first approach is the MEP guided stimulation. Obviously, this was probably the first studies were performed on the motor area, because it was known that giving the TMS in the motor area was evoking the peripheral response. So the MEP guided stimulation was based on the best position, on the best hotspot that was provoking the peripheral response, and on the intensity that was based on the resting motor threshold, so which is the response that gives that is the threshold that gives the peripheral response. It would be somehow the proof that we are sure that we are stimulating enough the brain to have a response. The negative part of this, I would say not negative, but the limitation of this approach is that it's limited only to the motor cortex, obviously. And I just added the fact that the MEP response does not imply that there is an activation with good signal to noise ratio in EEG. This is just a speculation. Then there is the different approach, is the MRI guided approach. I didn't put in also, I could have said also EEG or MEG guided approaches, which are the approaches where we stimulate based on some other experiment where we have identified some brain areas of interest that we want to stimulate. The biggest problem of this approach is that we have no idea what is the right intensity to stimulate other areas but the motor one. And even if we adjust all the stimulations of the other brain regions based on the resting motor threshold, it doesn't mean that the excitability of other brain regions are directly proportional to the resting motor threshold excitability in all the subjects. So we can have very spurious results. Then there is the third approach, the last one, which is EEG guided, completely EEG guided approach. This is an approach that I have seen done only by a couple of groups. And what they do is to find the hotspot and the direction of the coil and the intensity of the coil that maximizes the EEG response. So it's a TMS EEG guided by the best response in EEG. Usually what they do, they stimulate the brain in different positions, different area, in the same area, but different positions of the coil, different intensities for approximately 10, 15 times. And then if they see a response that is local, very local response, and that shows a big asymmetry between the two hemispheres, for example, then they stick to that position, and then they choose the intensity that is the minimum intensity that still can elicit the response, and then they perform the experiment this way. Somehow the part that it still has to be investigated is what is actually this response. Because, for example, from some tests that we have done, the best response in the motor area doesn't really correlate with the best resting motor, the best hotspot for evaluation of the MEP response. And another problem is that this approach can be used only in the brain regions, only over the brain regions that are not somehow overlapping or are not the spot of stimulation is not producing a strong muscular artifact, because the muscular artifact covers their signal, and they are not able to then to tune the coil and the stimulation properly if everything is covered in the first milliseconds by the muscular artifact. So I want to summarize these three approaches. And what is interesting to me is to show is also how N100 is different in these two approaches, and how the curves are different in the first milliseconds, how much bigger is the response in the first milliseconds in the EEG guided approach compared to other approaches. Which means that probably the cleaning procedures and all the post-processing should somehow be different. And I don't still have the best answer to what is the best way to perform it. The EEG guided approach is definitely intriguing, but still there are many questions to me that have to be answered in both situations. So I would just I would like just to also say that the sham is important to know when our results are somehow reliable or not reliable, and I think this is something that has not been properly addressed in the past, and I have no doubts that 99.9% of the papers have identified right answers to their questions. But just to keep in mind that, for example, in the red boxes in this figure, the PEP, which is the peripheral response, but elicited in the cortex, can mislead or make us misinterpret our results. So I'm concluding by saying that we need some more steps to have a more stable and reliable technique in the future. And one of these steps is to use EEG optimized coils. Mainly, I'm thinking about more silent coils or coils that can be more focal and not stimulating a large part of the scalp to be efficacious. Because as probably Thomas will tell you later, the muscular artifact is not an easy thing to deal with. And then the scientific development is needed also from our side, maybe to understand better what are the biological mechanisms that we're actually looking at, or we are expecting to be responsible for the traces we see more deeply. So with this, I want to thank you for your attention and to apologize for not being able to share properly my slides.
That's totally fine. Thank you, Dr. Tomasevic. We're going to take one really quick question and then move on.
Just one really quick question. Concerning noise masking, how do you mask the bone conducted noise?
So the bone conduction, we usually use a foam, which is a soft material that we put between the coil and the cap. And this usually absorbs a little bit. So actually, to measure this, it's not so trivial. But I think that with a good foam, you can suppress it at least for a big portion of it.
Okay, great, awesome. Thank you again. I'm clapping on behalf of everyone. I'm sure no one can do that.
And you guys can keep the questions going in the chat. But in the interest of time, we'll move on to the next speaker. We're glad to have in Dr. Tomas Mutanen from Aalto University in Finland, who's going to talk to us about cortical modeling-based methods for non-invasive brain stimulation and EEG. So take it away.
Okay, thank you very much. First of all, can you hear me, and do you see my slides, like not my view, but the actual presentation view?
Yeah,
okay,
everything is all set.
Great, everything is running. So thank you very much, first of all, the organizer, for inviting me. Really nice to have this chance to talk about these methods that I've been developing with my collaborators over the past few years. And it's getting now, it's already over midnight, but what's better than to discuss artifacts and noise in this time of the day. So I'm currently working as a postdoctoral researcher in the Department of Neuroscience and Biomedical Engineering in Aalto University, Finland. And the title, I'm going to tell you how you can benefit from applying forward and inverse modeling of EEG for removing non-invasive brain stimulation related artifacts and noise components. Because of my background in mainly TMS and TMS-EEG, the examples that I will show will come from the TMS-EEG world, but I think that the principles and ideas could be also used for TDCS, TACS, EEG data, if you think about the strategies, how to apply them. So, so this is the outline for my talk. So first, I will very quickly define the overall problem with TMS-EEG data or recordings. Leo just did a really nice job in paving the way for this presentation, so I will not spend too much time in that. I then wish to motivate you why it is a good idea, or how we could benefit from modeling the cortical generators for EEG signal. And then I will cover two, in my opinion, good examples that show you how this source modeling can benefit the artifact rejection techniques. Then it's time for conclusions, and if I still have time, I can give you a couple of practical tips. Probably I will not have, so if anybody becomes interested, I suggest to contact me by email, and we can discuss later on, or maybe in the questions and answers part. Okay, so the crash introduction or crash course to TMS-EEG. Obviously, the idea is that we are using the electromagnetic induction to induce this strong electric field in the cortex to actually directly activate the neurons in the cortical region of interest. Then by combining the simultaneous EEG with this TMS technique, we can then, for instance, record how this initially focal activity spreads to different cortical regions, or measure the changes in cortical reactivity in different conditions. The problem, however, is that the electromagnetic induction, it induces electric fields everywhere, not just in the cortex, obviously. So as Leo mentioned, for instance, the tissues in the scalp, like muscles, they are affected by this pulse and causing muscle twitches. The electrode skin interfaces can be affected, and even the amplifier can be affected. So overall, the TMS EEG is a challenging technique with a lot of potential issues, artifacts, and noise sources that you need to deal with in order to really get to study the signals of interest, the good stuff. So why would you then want to start by modeling the cortical generators of EEG for removing artifact and noise? And the reason, in my opinion, is that well, obviously the sources for our signals of interest are intracranial. They are the postsynaptic currents in the cortex that then generate this volumic current in the whole tissue and in the head. And we can record and monitor these postsynaptic sources indirectly by recording the potential differences on the scalp due to these volume currents. The volume currents, however, they need to travel through the skull, which is an insulating surface, especially compared to the scalp and the brain. And really, this contrast between the conductivity of the skull and the brain makes these intracranial sources quite characteristic. So first of all, the topographies, if you look at them, they are quite smeared. They lack high spatial frequencies, and for many noise components actually and artifact components, this can be a little bit different. Not to all components or possible sources, but to many this is different. So if we are able to take this prior information of how the intracranial EEG sources, how we expect them to look, we can use it in multiple ways in figuring out which parts of the signal are noise and which are the real signal, and then also in the removal process. So basically, if we can write our measurement in this form, where S stands for the signal and X stands for the unknown brain sources that we have, A is artifact and N is noise, and then L is the lead field matrix. It basically contains all the information of our forward model. It describes how all the possible sources in our cortex would be mapped onto the EEG system. So if we are able to calculate this lead field, then this opens up a lot of possibilities that I will discuss more thoroughly just in a minute with few examples. So this is basically the tough step. I will not go in too much or not at all into details how you can estimate this, but there's obviously a lot of material how you can do this in practice, for instance with field trip or many other tools to calculate this lead field matrix for EEG. So the first example that I'm going to show you is actually the TMS related muscle artifacts that Leo was suspecting quite correctly that I'm going to talk about. So as Leo nicely explained, when the TMS pulse, it also quite often it activates the cranial muscles, and this creates quite a characteristic response in the EEG signal that you can see on the left. So there is usually this short-lived biphasic response with fairly high amplitudes compared to the neuronal signals. And on the bottom row left side, you can see the topographies of the during the time of the muscle artifacts. So already from here, you can kind of see some things resonating with what I said just a few slides back, that these topographies, if you have a forward model or you would do some modeling of EEG, these topographies, they don't really look such that they would be likely to originate from intracranial postsynaptic sources. On the right panel, the main information for you for this presentation is just the kind of overall map of where you usually get these artifacts. So quite often you can quite safely stimulate the cortical spots close to the vertex of the head, but the more lateral you go, quite obviously the bigger artifacts you create by stimulating the large cranial muscles. Okay, so if the muscle artifacts have quite different topographies than most of the, or let's say in general, the intracranial neuron sources, then we already almost have the solution already. So we can approach this problem by estimating the topographies, the most significant artifact topographies of the muscle responses, and project them out. So we could use for this, for instance, a method called signal space projection, which is basically mathematically analogous to removing noisy channels from the data. Now, in this case, instead of removing single channels, we remove topographies, but the topographies, they can be written as a linear combination of the original channels. So whenever you remove a topography, you reduce the dimension of the signal with 1. So in a sense, it is analogous to removing channels. The tricky step here is then to figure out how you could, you need to figure out a strategy to find these artifacts from the signal. And an approach that we have used is based on the looking at or inspecting the frequency spectrum of the artifactual data. So on the right panel, you can see now the time frequency transformation of a typical artifact contaminated EEG channel, and you can see that right after the TMS pulse, there's a really broad band going up to the basically the maximum frequency that this sampling or this amplifier allows. And then quite soon after the pulse, we can see only responses below 100 Hertz. And these later responses are then most likely actually reflecting genuine responses, and we know quite well that the EEG is mostly consisting of, or the neuronal EEG is mostly consisting of frequencies below 100 Hertz. But the problem with the muscle artifact is that you cannot simply low pass filter the data, because there are also a lot of components that are then overlapping in frequency with the brain responses. So we actually use maybe a somewhat unintuitive strategy. So first, what we do is that we high pass filter the data to get rid of all the brain responses. And now we do the assumption, the big assumption, that the high frequency components of the muscle artifact actually have similar topographies and are lying in the same signal space as the whole muscle artifact. And if this is the case, then we can now estimate the topographies using singular value decomposition from the high pass filtered data, and then project them out with the SSP from the original data. And this was already tested on 2011, or tried for the first time by Hanna Mäki and Risto Ilmoniemi, and you can quite quickly see that, okay, you are able to remove the muscle artifacts. We do get rid of these big biphasic responses. But it's also quite obvious when you look at to the right side that we are also causing a lot of distortion to the to the brain responses. And the reason is that we are now removing, as I said, we are removing the linear combination of channels, so topographies from the original signal. So it can distort the signal in quite an arbitrary way. And it makes it difficult to interpret and analyze later on. So then the solution that we suggested a few years later is something we call source-informed reconstruction, and this is now very much based on this forward and inverse modeling. So how this works is that first we do the exact same step that I already explained to you. So we estimate the artifact topographies from the high-pass filter data, and we project them out. On the left, you can see also the math. So really, the equation doesn't change in any other way except we multiply it with this linear operator P, which projects out the artifact topographies. This is not such a bad case as the data that I showed earlier on, but there is still some distortion in the signal. But what we can do now is that if we look at this data, we realize that it's actually the form is exactly the same as in the original case. The only difference is that we have now multiplied it with this known matrix P, and we can, of course, at this stage we assume that the PA is more or less 0. So we get this is the result from the previous step. But this is still like this is just the artifact-free standard form of EEG recording. So actually we can use standard ways to estimate the cortical responses that would produce this PS signal. And now the next step is to calculate the minimum norm estimate that would produce the projected signal. And once we have the estimate for the cortical activity, we have already this lead field L, because otherwise we couldn't have calculated the source estimate. We can now calculate backwards how the signal would look like in the original signal space. So we can now see that this is obviously quite a nice example data. So it has just the correct size muscle artifact. That this still works quite nicely, but it is a nice example that in some cases it is possible to first project out the muscle artifact and then nicely reconstruct the neuronal signal. And this is just to highlight that this whole process, you can just write it with one equation. So this would be obviously very simple for anybody to program in MATLAB once you have calculated the lead field or the forward model for your EEG. This is another real TMS EEG dataset that we have processed with this method. So the red curves, they show the artifactual data, again showing these large biphasic responses in the beginning, and then the black curves show the signals that we are able to recover under this muscle artifact contaminated data. And now if we look at these topographies, again keeping in mind what kind of topographies we would expect to see from intracranial sources, we can already see from here that these first responses in the original data are not likely to originate from genuine post-synaptic current. Then on the other hand, after we have removed the artifact topographies, we are able to uncover topographies that have much more of these low spatial frequency type of characteristics. And in this study, we actually went one step further, and we used kind of we approached this data from another direction, again through modeling. So we assumed that, okay, you could assume that the first response would be coming from the location that you stimulated primarily. So we placed a dipole to the same spot where we stimulated, which we know from the neuronavigation, and then we modeled the topography that would result from this focal activity. And I think it's quite nicely matches the topography is the first topography that we were able to recover from this data. Just a quick note that this SSP-SIR method is completely generalizable for many problems. As long as you can find again a strategy to estimate the artifact topography. So this is just an example that I will not cover to or not at all in this session, but here we started with Manabiabani and Nigel et al. If you could estimate from sham data the topographies for these peripheral responses that Leo talked quite a bit in the previous presentation, and I think it still requires some work, but the results are at least promising to some extent. Then I have few minutes, maybe 1 minute left, so I will quickly show an example of another method where we use actually even more of the ideas that I was promoting in the beginning. And this is called the sound algorithm, which we developed for automatically finding or detecting and rejecting noise. And the idea is very simple in the end, actually. So we start by estimating the noise levels in all the channels. So, well, in each channel separately. So, for instance, in this example, we are now looking at this channel, and we exclude it from the analysis for a moment. And we use actually the information in all the other channels. And again, using standard minimum norm estimation techniques, we calculate the most likely cortical current that would have generated the signal in all the other channels. And now from these cortical currents, we can then calculate that what is the most likely signal in this channel of interest. And if there is a discrepancy between the actual recording in this channel and then the estimation that is based on the other channels, then we regard this channel as noisy. Now on the next step, we proceed to some other channel and estimate its noise. In this case, we do still use this channel, but the trick is that in minimum norm estimation, you can actually regularize the solution for noise. So because we now know that this is noisy, we weigh it less in the estimation, so we don't use it so much, and therefore it doesn't contaminate the next estimation. And we do this iteratively few times to get reliable estimates. And finally, when we have estimated the noise levels in all channels, we can take the whole data that we have, all channels, calculate the most reliable minimum norm estimate we can find, because now we have a good idea of how the noise is distributed. And from this minimum norm estimate, we can reconstruct the signal back and remove a lot of noise. And this is just to show that it actually works very well. So on the top panel, we have the original data, and on the B top panel, you can see how we have detected and removed this noise. And on this D panel, you can see that also the noise estimates, they correspond quite nicely to the original data. So to conclude, I think it can be this type of forward and inverse modeling of EEG can be highly beneficial for removing artifacts and noise from TMS-EEG recordings or NIBS, possibly NIBS-EEG recordings. You can use it to correct distortions in the signals of interest if you know how the distortions are defined, as in the case of SSP. You can use it to evaluate the success of the data cleaning when you are lacking the ground truth. That has been mentioned many times today, that it's very difficult to assess these techniques when you don't really know what the ground truth is. And the sound demonstrates that you can use these to automatically differentiate between noise and signals of interest. And then ultimately, obviously, your goal is to reject the noise. So the most important slide, of course, is to acknowledge all the important collaborators in the alphabetical order who have contributed in developing these methods over the years, and then also all the funding bodies that have helped me to conduct this work. And now if somebody got interested and wants to get some practical tips, I suggest to send me email later on, just because it's getting late, and I think we are overdue.
Yeah, we are behind the schedule. Wonderful. Thank you so much. It was such a great talk. Let me guess Daniel Manon is asking a question. Let me unmute. Okay,
Yeah, we'll do
so
one quick question and then we'll wrap up.
you go ahead and ask your question.
Okay, yeah. Well, I think one explanation that has been suggested is that it is like the electrode skin interface gets depolarized if you don't have good enough impedance. You have high impedance, the interface can be depolarized, so the charges get actually accumulated, and then it exponentially goes back to the baseline. These can be really tricky. So in this case, if you have only few channels here and there, this type of spatial interpolation techniques as sound, they can be really effective. Sometimes they can be really persistent, and you can have them in many channels, and in those cases it can be really tricky. So sometimes ICA, I think independent component analysis can find quite a good match with the exponential, but oftentimes it's often also really difficult. So I cannot give you a better answer at this point.
All right. So with that, I'd like to thank all the speakers. This was really a great session, and it was really informative for me. I hope it was informative for all of you. If you have any more questions, feel free to reach out to the speakers directly. I'm sure they'll be happy to email you back and chat. So I just want to thank everyone. I'll leave the room open a little bit in case you guys want to chat for a few more minutes, and then I'll close it. But again, thank you to all the speakers. This was really great. Hopefully we could do it again some other time. I know it's late and you guys are all over the country, so please stay safe and have a good night. Thanks, everyone.